Hello and welcome to lesson 5.4, the cross product and its applications. So today we're going to investigate another type of product between two vectors called the cross product, or sometimes also called the vector product. The cross product of two vectors is the vector that is orthogonal to both of the original vectors. So note, the cross product can only be applied to three-dimensional vectors. Also, if you're interested in finding out this information on how to actually come up with this cross product, you can look at a supplementary document. So, the cross product of the vector u, we'll call it by ABC, and the vector v, given by the components d, e, and f, can be calculated as u cross v is equal to bf minus ce as the first component, CD minus AF as the second component, and AE minus BD as the third component. You can memorize this formula. You can also memorize on how to calculate this in a different format. And again, the proof of this formula is found on the supplementary sheet within this section of that course. You can look at that at any point in time. But I use an easy way to remember this. So what I do is I set up a matrix like this. So I set up the matrix having the first vector listed twice in a row. So ABC, ABC, and the second vector DEF, DEF. You can add the IJK above. So what you usually do is you go from the I down to the right, and you cross B and F first. So you take B, you multiply by F, and then you come across to the other I and come down towards the left now, and you cross C and E. So you take BF and you minus CE, which you can see right here. Next time, you take C and D, and you subtract AF. Last, you do the same thing, AE minus BD. There is other methods to calculating this cross product. These are the ones that I'm going to show you in this class, but if you'd like to investigate other options, you're more than welcome to. I've seen some people truncate this A, B, C, D, E, F and organize it in a different format and use that. I prefer to use this. Okay, so we're going to determine a vector that is orthogonal to 2, 3, 4, and 5, negative 7, negative 9. So in other words, we're looking for the cross product between these two vectors. Off to the side, I'm going to write the 2, 3, 4, 2, 3, 4, like I suggested, and the 5, negative 7, negative 9, 5, negative 7, negative 9. So first I take 3 times negative 9. 3 times negative 9 is negative 27. I'm going to subtract 4 times negative 7, which is negative 28. Next, I'm going to take 4 times 5, which is 20. And I'm going to subtract negative 18. Finally, I'm going to take 2 times negative 7, which is negative 14. And I'm going to subtract 5 times 3, which is 15. So this result turns out to be 1 and 38 and negative 29. What this does is it generates one vector that is orthogonal, which is, in this case, 1, 38, and negative 29, which is orthogonal to both 2, 3, and 4, and 5, negative 7, and negative 9. If you want, you can prove this by dotting the product between 1, 38, negative 29, and 2, 3, 4 to get 0, 0, 0, or to get just 0, and same thing with the other vector. Okay, some properties of the cross product. If you work out u cross v, and you work out v cross u, you actually find out they're opposite directions to each other. Also forms a distributive property. So u cross v plus w is u cross v plus u cross w. Same thing if you put the vector at the end. If you take the cross product and you find out the cross product actually equals the 0 vector, that means u and v are actually collinear with each other, or u can be described as a multiple of vector v. And it is, again, associative. So it doesn't matter if you multiply the constant by the cross product or by any part of it and then apply the cross product afterwards. Okay, since the physical problems that deal with the cross product deal with an orthogonal rotation, then the direction of the rotation from u to v of the cross product relates to the rotation of the angle based on the right-handed system. That is, if the angle is counterclockwise, the cross product points up. If the angle is clockwise, the cross product points down. And sometimes, since you don't know what the actual size of the vector actually is, if, let's say, you were just given the magnitude, you use another vector that is called a normal vector. So some of your answers, you will see it being multiplied by a normal vector if you don't know the actual direction. If you know the size, you can work out the sizes easily. It's the direction that might be different. So let's talk about this physical rotation that I'm talking about. So let's say you're taking a vector u and you're crossing it with a vector v. So you're actually working out u cross v. Well, what you're doing is you're going from u to v. So you put your hand, you take your right hand and you place it, your wrist along the vector u, so that your thumb is at this corner right here. The thumb is either pointing upwards or pointing downwards. Now, if you can curl your fingers towards the vector v naturally, and you point your thumb, that'll actually tell you the direction of your point, or your direction of your cross product. So in this case, as you're curling your fingers from u to v, you have your actual wrist and your thumb pointing downwards. So this one is going downwards, or some people also say inwards. As with the example above, you have u cross v going this direction. So you put your hand along the vector u. You can curl your fingers towards the vector v easily by putting your thumb upwards, just like what the drawing shows. So the direction of your cross product actually goes upwards, or out of the page if you wish, or outwards. Okay, so another formula for the magnitude of the cross product with an angle of theta in between u and v can be calculated by u cross v magnitude is equal to the magnitude of u times the magnitude of v times sine theta. As you can see, one application of this cross product is to actually determine the area of a parallelogram. So over here I've got a parallelogram subscribed by the vectors u and v, where u and v have an angle in between them of theta. The height of this vector, or the height of this parallelogram, can be calculated by the magnitude of u sine theta. The length of your parallelogram, or base length, can be calculated just by the magnitude of v. So the area of your parallelogram, if you remember from grade 9, is base times height. So the base in this case is the magnitude of v, height is the magnitude of u sine theta, or can be rearranged to the magnitude of the cross product. Okay. Torque is another measurement of a force acting on an object that causes it to rotate, given by either this formula or this formula. So, one point of note, usually R is measured in meters. The vector F is usually measured in newtons. And therefore the vector T is measured in Newton meters, not joules. Okay, so a force of 60 newtons is applied in a clockwise direction. So it's being applied in a clockwise direction, so that means it moves from here to here. At an angle of 80 degrees to the handle, 20 centimeters from the point of rotation. So here's where it started, this is where it ended. And this is 20 centimeters. Calculate the magnitude of the torque. So to calculate the magnitude of the torque here, we'd be using this formula. So the point of rotation is 0.20 meters. Our force being applied is 60 newtons. And the angle of rotation is 80 degrees. I'll grab my calculator and plug this in and work it out. And I get this as about 11.818 Newton meters in size. Now, by using the right-hand rule, I can determine in which direction the torque vector points. So using the right-hand rule, the torque vector points inwards. Because again, I place my fingers along this vector where the 20 centimeters is. I can only naturally rotate my fingers towards the to the end spot. and therefore my thumb has to point inwards. Okay, so some other applications of the cross product. The volume of a parallelepiped, which is drawn over to the right here, can be calculated by finding the magnitude of the triple scalar product. So let's say this parallelepiped is defined by vectors A, B, and C, all coming out from one starting corner. Now the triple scalar product, to find this volume right here, can be used to calculate the triple scalar product. So the magnitude of the triple scalar product. So I put absolute value signs on this first. The triple scalar product is the cross product and dot product of these vectors in any order you wish. So it could be A cross B dot C, could be A dot B cross C, whatever. Now please realize whenever using the cross product and the dot product, cross product actually supersedes the dot product unless it is placed inside of brackets. So you first have to perform the cross product here before you can actually work out the dot product. And the volume of a tetrahedron is 1/6 the size of a parallelepiped. So the volume of this case, if this was the same vector C and this was the same vector B and the same vector A, let's actually move C over here. Then in order to calculate this, you're just doing the 1/6 that magnitude of A cross B dot C. And then you just calculate from there. Thus concludes this lesson.